So one thing we want to be able to do is combine two-point test crosses, the data from those, into a map that has more than just two things in it, right? So our two-point test cross tells us if two loci are linked, and if they are linked, their relative distance, the percent recombination, the map units, whatever that it is we've calculated. So here we're working with a table, right, of two-point test crosses. And so, like this part here, whoops, right? We had the dihybrid test cross, and the recombinants were equal to the parentals. And so there's 50 map units. It looks like independent assortment, and it might be independent assortment. And here, right, in this cross, that's the AF cross. So we had an AF dihybrid times the AF double homozygote recessive, and we found 10% recombination. So there's a 10 in the table. So, well, I've circled 10, so let me start there. Ordinarily, I would recommend starting with the smallest number, and I'll do that on the next one. But I'm looking at this table, and I'm seeing that everything along the A line is 50 except for F, and everything along the F column is 50 except for A. So what that tells me is that A and F are linked to each other, but they aren't linked to anything else in this table. So all of the genes in the table that were given of these two-point test cross results are not necessarily linked to each other. We might have more than one linkage group, right? So we might have little clusters of things that are linked. So to show that, it's supposed to be an F, I would draw something like this, where I've got a line that's supposed to represent a chromosome and a little dash on there that's supposed to represent a locus, and that's where A is and that's where F is, and they're 10 map units apart. All right, so that takes care of that, right? Nothing else is linked to it because of all these 50s. They're not linked. They could be on the same chromosome. They could be on totally different chromosomes. We have nothing that links them to one another because we see the signs of independent assortment. 50 is never on the map. If you find yourself writing down 50, you've done it wrong. Stop, regroup, back up. You should never have a 50 in a map. Okay, well, let's go to the next small number, 5. So D to E is 5. I can write that down because I know that's the smallest number on the whole table, so nothing can be in between D and E. Now I see that C and D, so the next thing I'm going to do is look for things that involve D, pairs that involve D, or pairs that involve E that are less than 50. And my next smallest number in the table that I haven't taken account of, right? I've taken care of this 10, is this 28. And C to E is 28. Okay, so C to E could be 28 out here, or C to E could be 28 out here. And I tell that by checking the C to D distance. C to D is bigger than C to E. That means that C must be closer to E, right? Because the C to E distance is smaller. So that distance must be smaller. So that distance is smaller, so C is closer to E than it is to D. Now notice that 28 and 5 adds to 33, but we have 32 in the table. That's because there's double crossovers. And the further apart things get, the more likely there are to be double crossovers. And each double crossover makes it look like there was no crossover. Any even number of crossovers between 2 points will look like no crossovers, and any odd number of crossovers between 2 points will look like one crossover. So the further apart we get, the more likely we are to get double crossovers that eliminate some of our crossovers. Really, there are two. If we want to count crossovers, remember that's what we're trying to do. We are trying to count the number of crossover events because it's the number of crossover events that is proportional to distance. So we are losing 2 crossover events for every double crossover. It looks like there's none, but really there were 2. So the further apart things get, the more we're going to underestimate. So we use these distances not to put on the map. Notice I didn't write 32 down. I don't write that 32 down. I use that inside my head to know that C goes on this side of E and not on that side of E. And I understand that 32 is likely to be smaller than the actual additive amount of 33 because of these double crossovers. And now I've taken care of all the little numbers in the map, right? 10, 5, 28, 32, I use that. And I know it's something that I don't write down. Now, do I have everything on here? No, I do not. I do not have B. Here, let me get a different color. Right, so if I look at B, that was a poor choice of color. It's not very visible. So I'll scribble a little bit. Now notice that there's nothing in the diagonal. That's because B times B wouldn't tell me anything, so it's not going to show up in the tables. But B times A, B times C, times D, times E, times F, that is all 50. So B is not linked to anything. Go back. So B is its own little linkage group. So I have 3 linkage groups. I have 1, 2, 3 linkage groups. Groups of genes that are linked according to the cross data here. Now, who knows? They could all be on the same chromosome. They could be on different chromosomes. We don't know. So we show them separate. Remember, there's never a 50 in the map. And also, it doesn't matter. I could have written F10A, and that would be the same, right? There's nothing left to write in here. I could say C. Oh, sorry, I've got to get rid of that color. Here, let me use my eraser. All right, let's see what would be a good color. Here, this will look different. I could say C to E to F, and that would be 5 and 28. And notice that I used a different mapping convention. Here I used a line with hashes and then the numbers, and here I use a disrupted line with here's my C gene and a line that's 28 map units long, and E, and a line that's 5 map units long, and an F. Either of these are fine. Those are the 2 common ways that people write it out. And notice that this is the same as this because we have nothing to fix them in place. And so there is our map. We have A to F is 10, B is by itself, D to E is 5, and E to C is 28, and that is a linkage group. So now let's do the next problem. Notice that I have a slightly different form of table. We don't want to be thrown off by things like that. We want to realize that, okay, it's a table of 2-point test cross results. So like this first one, that would be the dihybrid times, it's a little weird. Why do I have a little delay in there? That's funny. So that's where this 19 comes from. There was an AB dihybrid times the AB double homozygote recessive, a test cross. And I found and they found, whoever did this, a 19% recombinance, right? And that's what's happening with all of this. It's just a slightly different display. So like here we got a lot of numbers that are less than 50, right? And we'll have various amounts of linkage in our tables. So sometimes maybe everything is less than 50 or almost nothing is 50, and sometimes almost everything is 50. So we just have to deal with what we get. So I start with whatever's the smallest thing. So C to E is 5. And I can write that down because if it's the smallest number, then nothing else is going to be inside of that. So now I want to look for other small numbers that include C or E. So here's A to C is 21. A to E is 23. Ooh. All right. And I'm doing a quick scan here to see if any other numbers that involve C or E are smaller than that, and there are not. So I'm going to work with those numbers. So A to C being 21 and A to E being 23 tells me that A is closer to C than to E. So I am going to put A there. All right, great. So those are taken care of, right? Those numbers, I've done something with each of those numbers. What's my next smallest number? Oh, A to F is 8. What's F to C? F to C is 27. Oh, good. So that's where F is going to go. And I don't know, maybe there's going to be something else out here. And if there is, I'll just bend my map. Okay, so that's taken care of. C to F is 27. That's taken care of. And right, this additive would tell me that, because I used that to figure out that F went here. So this suggests that C to F should be 29, but they're not going to be additive because of the double crossover taking away, making there be crossovers that we can't count. So we wouldn't expect this to be additive in the real world, or even in things that pretend to be the additive world, like this. Okay, so let's continue. Well, here, this B to F is 13. So A to B is 19, and A to F is 8. Yeah, I'm going to have to make a bendy map. So that's taken care of, and that's taken care of. Right, I just checked that to be here. Now, because I'm going from smaller numbers to bigger numbers, I should not, I mean, I might have run out of paper space and needed to bend, but I shouldn't need to adjust my map because I shouldn't find later that, D belonged in between A and F because I'm working up the pattern of numbers. And let's see, B to C, I don't need that anymore. B to E, that's taken care of in this map. It's like already included. It's consistent with this map. All right. So things that I've not taken care of yet. So let's think about that. Here I've come upon C to D is 33 and D to E is 31. So D is closer to E than to C, right? That's what these two numbers tell me. I have a smaller number between D and E than between C and E. So I'm going to put D out here 31 map units away. All right, D to F is 50. Well, that makes sense, right? Because if I add these things together, even taking a little bit away for double crossovers, that is more than 50. So that's going to be far enough away to look like independent assortment. And B to F, same thing. D to B to D, excuse me, that's going to be even farther away. So those are not a problem, right? That's we would expect. And that's why we're doing these 2-point test crosses. This is what we're hoping to happen, right? Because 2-point test crosses, you don't have to get very far away on the chromosome before it looks like independent assortment. But if you can kind of stepwise your way out through a series of different genes, different loci, through different 2-point test crosses, then you can get a longer map with more things in it. And E to F is not a new thing. I've already got it in the map. Let's see if that number makes sense. 28, 21 and 8 is 29, and 5 is 34, and this is 31. So that's perfectly consistent with this map because we would expect the longer distances to be a little shorter than they should be. So we are done. And if we scroll down, that is consistent with the answer. Yes. Okay, so there's two more on this problem set for you to do for practice. So give those a try on your own and then check your answers.